Hello! Thank you for stopping by this talk on the power of many samples in query complexity. I'm Weiyun, and this is joint work with Andrew Bassilakis, Andrew Drucker, Mika Göös, Lunjia and Liang Tan. This talk will be given jointly by Lunjia and myself. I will start by introducing the setup of this work and our main result. Then Lunjia will discuss some applications of our main result. So this talk is about query complexity, where we have a Boolean function f, and we consider query algorithms such that, given an unknown input string x, query the bits of x one at a time, and finally output a guess on f of x. Here we ask, how many queries are needed in order to compute f of x? The answer to this question is called the query complexity of f as a measure of how complicated f is. In this talk, we will particularly focus on the randomized version, which we denote by R of f. The randomized query complexity is famously characterized by Yale's minimax principle. A bit more formally, R of f is the least number of queries needed by a randomized algorithm on the worst-case input x in order to output f of x with probability at least 2/3. Here, the probability is over the random coin flips of the algorithm. Yale's principle relates R of f to the distributional query complexity of f. Formally, the distributional complexity of f with respect to an input distribution script d is the least number of queries needed by a deterministic algorithm on input x, drawn from script d, in order to output f of x with probability at least 2/3, where the probability is over script d. Here, we can assume without loss of generality that the input distribution script d is balanced. This means that a half of its probability weight comes from some distribution d0 on inputs that evaluate to 0, and the other half from some distribution d1 on inputs that evaluate to 1. So one can also think about the distributional complexity as a task of distinguishing between d0 and d1. Now, Yale's minimax principle says that R of f is equal to the maximum distributional complexity of f with respect to d over all input distributions d. In other words, Yale's principle characterizes the randomized query complexity by the hardest distribution pair d0, d1. For example, for XOR, it's known that the uniform distribution is hard. To recap from the previous slide, we can think about distributional query complexity as the following task. Given an input sample from either D0 or D1, a deterministic algorithm needs to decide which is the case. It turns out, for some input distributions, this task becomes much easier if we allow query access to multiple independent samples from either D0 or D1. Such examples were studied by Schautiel in the context of direct product theorems. So for example, consider the XOR function on n bits. It's well known that its randomized query complexity is exactly n. Now let's take a look at the following input distribution. With probability 99%, the first input bit is 0, and each of the remaining bits is uniformly random. For the remaining probability of 1%, the first bit is 1, which is followed by a single uniformly random bit and then all zeros. We can see that the distribution is hard 99% of the time. This is because if the first bit is 0, then the algorithm needs to compute XOR on n-1 bits with respect to the uniform distribution, which takes n-1 queries. On the other hand, the remaining 1% is easy, because if the first bit is 1, then querying just the second bit gives us the answer. So overall, Given a single sample from this distribution, the algorithm is likely to have to solve the hard case. So, the distributional complexity relative to this particular distribution is omega n. Now, on the other hand, if given multiple samples, then we can distinguish D0 from D1 with only constantly many queries. This can be done by querying the first bit for a large constant number of samples, which will give us good chance of encountering an easy sample. Alternatively, we can also see this by an error reduction argument. For this Shawty distribution, we have a simple algorithm with 49.5% error in a single sample setting that only queries the first 2 bits. We can then amplify the success probability to 2/3 by repeating this algorithm on fresh samples and taking the majority answer. This is a trick that only works in the multiple sample setting. Shawty examples tell us, among the hard distributions in the single sample setting, some become easier if we allow access to multiple samples. Then a natural question is, does having multiple samples help for any distribution? This is the main question we address in this work. Our short answer is no. And our longer answer is, for any Boolean function, there exist hard distributions that remain hard even with infinitely many samples. In this sense, these distributions are even harder than the other hard distributions in the single sample setting, such as Shawty examples. So more formally, we define the correlated samples problem for a Boolean function f and an input distribution d given by the pair d0 and d1 as the minimum overall case of the distributional complexity of f to the case with respect to the distribution 1/2 d0 to the case plus 1/2 d1 to the case. Here, f to the case is a function that evaluates k disjoint copies of f, and d0 to the case and d1 to the case are k-fold product distributions. So in particular, under the distribution 1/2 d0 to the case plus 1/2 d1 to the case, f to the case outputs either k0s or k1s. This distributional complexity to be minimized on the right-hand side describes the complexity of distinguishing d0 from d1 with k samples available. We can see this is a non-increasing function in k, because having more samples is only going to help. Also, for the interesting case, we only need to consider k being at most n. As an example, for Shawty's distribution d for XOR, we've discussed earlier that core of XOR and d is at most a constant. We also define a distribution-free complexity measure, core of f, which is core of f and d maximized over all d. In other words, core of f is characterized by the hardest input distribution in the multiple sample setting. We can view core of f as a counterpart to R of f in the multiple sample setting. The main result of this work is that, for any Boolean function f, which can be partial, core of f is equal to R of f up to a constant factor. That is, we show that there exist distributions that remain hard even with infinitely many samples. So for XOR, as an example, this says core of XOR is in theta n. So there are hard distributions that are much harder than Shawty's. Let me briefly mention a related problem called selection. For a Boolean function f and a distribution d, the selection problem is the task that, given a sequence of independent samples x1, x2, and so on, all drawn from d, output the pair I and f of xi for some index I. Here, the algorithm has the freedom to select one of the samples to evaluate. we can define complexity measures cell of f and d and cell of f in a way similar to the correlated samples problem. A similar problem called truth was studied by Weiyun et al. In the context of communication complexity. Just like the correlated samples problem, selection is also subject to Shawtiel examples. But it turns out that selection is strictly harder than correlated samples. In more detail, we show that for any f and d, core is upper bounded by cell up to a constant factor. Moreover, we show that there is a pair f and d such that it takes linearly many queries to solve selection, but only a constant number of queries to solve correlated samples. So from this, our main result implies for any Boolean function f, cell of f is equal to R of f up to a constant factor. Now I will hand over to Lunjia, who will discuss some applications of our main result.
Thank you, Weiyun. I will talk about two applications of our main result. The first application is proving composition theorems. Given two Boolean functions f and g, we can compose them so that the output of g is the input of f. Here, f takes n input bits, so we make n copies of g, and each copy corresponds to an input bit of f. Each copy of g takes m bits as its input, so the composed function maps n times m bits into a single bit. This figure shows how the composed function is constructed. Composition theorems care about the complexity of the composed function relative to the complexity of the two individual functions. Specifically, we are interested in this question: whether the composed function has randomized query complexity lower bounded by the product of the randomized query complexities of f and g. Recently, this was shown to be false for some partial functions f and g, but is still open for total functions. What makes this more interesting is that the deterministic version and the quantum version of this claim are both true, and only this randomized version is still unsolved. What I'm going to show you is that we can use our main result on the correlated samples problem to prove a version of the composition theorem where the randomized query complexity of f is replaced by its fractional block sensitivity. To give you an idea of how we prove this composition claim, let us start with a toy example where f has a very simple form. It maps the all 0 string to 0 and maps the all 1 string to 1. All the other inputs to f are considered invalid, so f is a partial function here. We only focus on these two input strings. It's quite clear that the fractional block sensitivity of f is 1, because the only sensitive block is the entire input string. Now, the claim we wanted to prove simplifies to that the randomized query complexity of the composed function is at least as large as the randomized query complexity of the inner function g. How do we prove this? Essentially, we want to show that computing the composed function is as hard as computing g. So we take a hard distribution for g and use it to construct a hard distribution for the composed function. Here's one way to do it. We take a hard distribution pair for R of g obtained from Yale's minimax and draw all the inputs x1 through xn so that they are equal and are from the hard distribution pair. This gives an input distribution pair for the composed function, and it's indeed hard because when all the inputs are equal, computing the composed function is equivalent to computing g, which is hard because we picked a hard distribution pair for R of g. This proves the claim. But I want to show you another proof which can generalize better when f is more complicated. Since we showed that core of g is the same as R of g, we only need to prove that computing the composed function is as hard as solving the correlated samples problem for g. To show this, we take a hard distribution pair for core of g, which exists by definition because core of g is defined by the hardest distribution. Now we draw all the inputs independently from this hard distribution pair, and if you think of these inputs as the multiple inputs in the correlated samples problem, you will see that computing the composed function is essentially the same as solving the correlated samples problem, which is indeed hard because we picked a hard distribution pair for core of g. This gives another proof. The two proofs give very different hard distributions for the composed function. In the first proof, all of the inputs are equal, but in the second proof, the inputs are independent from each other. I'm going to show you why this independence makes the second proof generalize better. First of all, both proofs can generalize to multiple sensitive blocks. Consider this function f that maps the all-zero string to 0. Its input is divided into 3 blocks, and flipping each block flips the output. For such functions, we can show that the randomized query complexity of the composed function is lower bounded by the number of blocks times R of g. Here, Bs is a shorthand for block sensitivity, which equals to the maximum number of disjoint sensitive blocks. To prove this, we just need to construct a hard distribution for the composed function, so that computing the composed function on that distribution requires R of g queries in expectation in each block. Again, we can construct such a hard distribution from either R of g or core of g. As before, the hard distribution from R of g gives equal input in the same block, and we also need the inputs in different blocks to be independent. By contrast, the hard distribution from core of g gives inputs that are all independent from each other, which are more suitable for proving a composition theorem with fractional block sensitivity. This is because in the definition of fractional block sensitivity, the sensitive blocks may overlap. When 2 blocks overlap, it's hard to make sure that the inputs are equal within each block, while inputs from different blocks are independent. But if all inputs are independent, this is not a problem. The same proof for block sensitivity can be used for fractional block sensitivity if we construct the hard distribution from core of g. This illustrates the power of the hard distribution for the correlated samples problem. The second application I'm going to talk about is called building hard distribution for all biases. When we define randomized query complexity, we consider algorithms that achieve success probability 2/3 on the worst-case input. Now we want to consider algorithms achieving worst-case success probabilities slightly larger than half, say half plus epsilon, or in other words, achieving bias epsilon. This is of course easier than achieving success probability 2/3, but we're interested in the reverse relation. Here is an inequality showing such a relation. For all epsilon, achieving bias epsilon requires at least epsilon squared times R of f queries. I'm ignoring constants here just for simplicity. This claim is simply by the Chernoff bound. If you have an algorithm achieving bias epsilon, you can repeat it 1 over epsilon squared times to get an algorithm achieving constant bias. Now, if we apply Yau's minimax theorem on the left-hand side, we know there is a hard distribution D such that achieving bias epsilon on D requires epsilon squared times R of f queries. One caveat of this claim is that D has to depend on epsilon. Different epsilon gives different hard distribution D. What we want here is a single distribution D that is hard for all epsilon. Such a distribution is indeed very useful and is related to our first application, proving composition theorems. In a very recent work, Shalaf Ben David and Eric Blaise used this type of hard distributions to prove a tight randomized composition theorem for partial functions. So the question is, how do we construct such a distribution? Here's one potential way to do it. We simply choose D as the hard distribution for R of f obtained by Yau's minimax, and hope that is also hard for all biases epsilon. In other words, we wish to show an amplification claim for this particular distribution D. That is, achieving bias epsilon on D requires epsilon squared times R of fd queries. However, this may not be true. Chatill's example shows a distribution where achieving epsilon bias only requires constant number of queries, but achieving constant bias requires n queries. To make this work, we observe that such an amplification claim becomes true if we replace the right-hand side by core of fd. Indeed, when we have multiple inputs, we can amplify the bias simply by repeating on fresh inputs. Finally, we apply our main result, which shows the existence of hard distribution D, where solving the correlated samples problem is at least as hard as computing f given a single input, and this achieves the goal together with the amplification claim above. To conclude, we started from Yau's minimax principle, which says the randomized query complexity is witnessed by a hard distribution. Shaltio's example tells us that some hard distributions are harder than others. To obtain a real hard distribution, we introduced the correlated samples problem and showed the existence of hard distributions that remain hard given infinitely many input samples. We showed that such distributions are hard for all biases and are useful for proving randomized composition theorems. That's all for this talk. Thank you.